Yeah, you can, I have a couple QR codes throughout the slides, so for my LinkedIn, but also for the files that I'll be using. I'll bring this back at the end of the screen, at the end of the talk, so don't worry, you don't need to rush. But basically, you can find on Dropbox like a little repo with a couple of notebooks, all the requirements and stuff like that. All right. Yeah, so we're going to talk about anomaly detection, but not just anomaly detection, but specifically in time series. And well, I'll start with convincing you that this is indeed a quite special problem, probably not what you're used to in other parts of the field. And we'll actually talk about quite a few major topics within this field, essentially going from introducing the problem, considering quite simple, low-hanging fruit type of solutions, towards sort of more advanced ones that can already really benefit you in practice. And maybe on a practical note, if you have like small clarification questions, don't hesitate to just like raise your hand. Bigger, sort of more existential questions, that's probably better for the end of the talk. All right? Okay, well, let's start with reminding ourselves, well, what is just anomaly detection in general? You probably have seen this picture numerous times. I believe it's from Scikit-learn, right? But again, a good reminder what anomaly detection typically is, right? Remember, we have a problem or we have a bunch of observations that are typically independent of each other, and our job is to find sort of the main cluster of what is normal, and everything outside of this normality is not normal, therefore anomalous, right? So quite a well-defined problem. The thing is, even though this definition isn't too different for time series, you'll see that the time component sort of completely changes this logic. So if you have a look at this series over here, that's actually what we'll be dealing with for the most of today. Essentially, now this is no longer about a bunch of independent points. More than that, they might not even come from different sources. In fact, there might be one thing over a period of time. So let's say we have one sensor measuring air quality in California. That's actually what this real data set is based on. If you get the files, you can find the source data. It's pretty interesting, good for our purpose, and I guess relatable for most of the people here. So essentially, a problem now becomes, let's say we have some kind of fluctuations over time. And like you see in this case, we reached a point in 2012. We look at the history and we see this sudden spike. The question is that normal? Was that expected? Is it anomalous? Right, so that's the kind of question we'll be answering here. And in fact, what I'm showing you here is what can be referred to as a future anomaly detection, right? So that means that something happens. We are supposed to say, is that to be expected, or is it anomalous? Is it worth some kind of extra investigation? Or like in some cases, maybe it requires some intervention, right? Like in the case of air quality index, most importantly, it's not just a proxy for pollution and air conditioning usage, it's also a proxy for forest fires, for example. So if we have a huge spike in, well, a decrease in air quality index, essentially that might indicate that the forest fire is happening somewhere that might require an intervention. Therefore, practical usage for this anomaly detection problem. That is to be contrasted with another type of anomaly detection in time series. I would refer to it as anomaly detection in the past, right? So that means that stuff has already happened. So we have already measured this air quality index. And then we can look at some particular moments in time in the past, like notice these two red regions. I kind of arbitrarily highlighted them, but they are indeed noteworthy in this case, right? So one is summer 2008, where clearly we see a rather unusual spike, right? So perhaps forest fires happened there or something like this. And another one is a drop in winter 2011, right? And you see typically winters have lower air quality, probably because of, well, essentially heating and all the other things, but perhaps also weather patterns. So basically, our goal here is to evaluate the whole past history as a whole and make conclusions from it. Okay, this is normal, and this is not normal at all. So to be contrasted with each other, both are related yet kind of different problems to be dealt with, and well, this is pretty much what we'll look at today. So let's summarize what are really the key distinctions for time series specifically, right? So in this case, We have the timing component, and all the observations can no longer be considered in abstraction from this, right? So I cannot really compare values in July with values in January. It just, the context is too important, and in fact, those are no longer independent observations. So, and this factor, while it might seem insignificant, it actually changes the whole problem and sometimes requires for completely new approaches, and this is where we can leverage our other techniques from a time series field to essentially utilize it for this problem as well, right? So as I say here, even though some anomaly detection algorithms might be tamed if you're careful and you introduce time as a variable in some form, but we'll look at this problem from sort of a fresh perspective and see how we can address it beyond what you maybe already knew outside of this field. And I'll start from, as I said, quite simple, low effort, not requiring a lot of domain knowledge, but perhaps already acquiring useful results, to sort of more labor-intense, domain-specific techniques that can give us perhaps more robust results in the end, but you'll see that it's really not so simple. In reality, you probably will want to use a combination of all these things, and as I always like to suggest, it's never a bad idea to start small and simple, see if this helps you, and then only complicate things as necessary, right? Rather than saying, oh, I'm not going to work in it unless I'm training a neural network, right? That's a bit of a constraint to make here. So starting with rule-based approach, right? So that's really the simplest you can think of here, and this is essentially a family of very different types of solutions. What essentially is here is that you have a definition of a rule, which has a form of if-else statement, right? So let's say if air quality index is higher than ever before, that is an anomaly, right? Okay, it can be more sophisticated than that. I'll show you a couple more, but essentially that follows this strict scripted logic, and this logic is something that you probably want to come up with. This can be both data agnostic or to some extent based on the data, right? And remember that our perception of the problem is already based on observations of this data in any case, so to be completely data agnostic with a rule-based approach, it's quite challenging, but something to keep in mind regardless. And as you see that we will not actually use any forecasting models, any sophisticated time series tricks. In fact, this can all be condensed to using some simple tricks with tools like pandas. I'll show you a few. All right, so let's consider the first simple rule, just to give you an idea. And again, this is a subject that we can dig in a long time, but my goal here is to give you an idea of what kind of rules you can expect to make and whether they're useful or not and what kind of problems might arise there. So the first rule I'm showing here is essentially if a given point is exceeding 80% quantile after year one, mark it as anomaly, right? It's a little bit more complicated, so you need to do some sort of expanding window to calculate quantiles. And as you probably noticed, right, we get this artifact in the second year just because we don't have that much observation, so that's probably not very informative here. Well, we can also say after year two, and then we'll get a bunch of these peaks over here, well, which is actually not too bad, right? And again, the intuition here and actually the meaning of the rule is the key. Perhaps it has some sort of important implications for the problem you're working on, for the, let's say, environmental regulations, or perhaps you know that if this happens, that this really requires action, then you have directly a rule that both alarms you, but also has an important meaning in reality. So it looks complicated, right? But as I said, actually, in terms of implementation, I'm not going to show too much code, by the way. I have a separate notebook with all the computations in it, but here's just an illustration to show that this is maybe not as scary as it might seem. And, well, in case you're familiar with pandas, essentially it breaks down to calculating 80% quantile over an expanding window, and then all you need to do is just dynamically compare the values with that cumulative quantile. Right, up next, another rule. So let's say we want to take the seasonality into consideration, right? So with historic quantiles, this is really just based on the historic extremes, right? While we might actually be interested not just in overall extremes, but seasonal extremes, right? So that's another consideration that's a little bit hard to address with rules. We'll see later where models can help us a lot more with it. Well, in this case, let's say I define a rule that says if an observation is 10% above last year's weekly value, so essentially air quality index in that same week of the last year, right, then perhaps that's worth an alarm. You can imagine that's a very sensitive rule, right, so probably going to produce a lot of false alarms. Yet, right, you can increase this fraction, and if it's, let's say, 50% more than last year, that is indeed quite alarming, right? So let's say if July this year has a 50% worse air quality index than the year before, that's definitely something to be alarmed. What you do notice here, though, and I think that's a property of most of the rules, it's this arbitrariness of the parameters that you select, right? Like why 10%, why 50%, why not just any other number? So I would say, while sometimes, as I mentioned, it might come from literature, regulations, or just common sense, right? Let's say if temperature falls below absolute zero, that just shouldn't happen, right? So something's going wrong there. But generally speaking, it's actually not an easy problem, right? So if you cannot validate, if you cannot get some sort of parameter optimization for your problem, that might be quite a risk, setting this up as your main rule for anomaly detection. Well, we can carry on with this forever, but essentially, again, keep in mind that all you need to do is to think of an appropriate rule that fits your problem, isn't too arbitrary, ideally is validated in a form, and even if you think that this will not be the main tool, usually I see in practice that this is a good thing to have, especially for some sort of capacity type of extremes, right? Let's say we used all of our, I don't know, water in a given storage, or we have exceeded some sort of regulations which indicate that there's a fire, right? So something that immediately calls for action, and that would make a good rule. All right, so that was the first and the most simple, perhaps. Let's move on to something a little bit more sophisticated, that is most importantly a little bit more robust towards things that happened in the past and a little bit less arbitrary as a whole. And I'll start with what I refer to here as error trend seasonality decomposition. And I'll explicitly make a step to not use any modeling here. We'll use models on the next step. So here to make a first lowest effort move here from arbitrary rules towards something a little bit more scientific. Essentially, I will want some simple, usually automatic filter-based decomposition of my time series. I'll show you in a second what decomposition means if you haven't seen it before. And basically later on, I will use this decomposition to have a bit more insight into what's actually going wrong. Now, there's probably 1,000 different tools you can use here. Again, this is also applicable on top of modeling that we'll discuss in the next chapter. But here I'll propose a simple tool, probably given the effort versus the reward you get from it, it's kind of a more efficient one. That is the seasonal decompose from stats models. You can see here that it's really quite trivial. It's a bit of a black box, right? So it's good to learn about how this is exactly implemented. Some form of automatic convolutional filtering going on there. But ultimately, you can judge whether the filtering worked or not based on this output, and the only thing you really need to consider is it a multiplicative model or additive one. I'm not going to dive too much into details of tuning this up, so what is more essential here is that we're using a method to take our original series, as seen at the top graph, and decompose it into trend, seasonality, and everything else, right, which is in this case residuals. So you see, this is a little bit sketchy, right, so the trend looks kind of interesting, but it's overall not really wrong, right? So it did pick up something that has definitely to do with the reality, and in this case, it also picked up the, you see, stable seasonality patterns, quite okay, I guess, and the indication for us that things are not going too badly, right, is the residuals. It's a multiplicative model. Notice that it's not around 0, it's around 1, right? And in this case, they do kind of seem more or less to be random, right? So it's a good sign that we are doing well with this decomposition. So the question is, why did we do all that? Well, again, to separate stuff that is predictable and happens sort of naturally and doesn't produce anomalies by itself from the actual sources of anomalies. And in this case, actually, residuals is where we will be looking for anomalies. So if we do something like a histogram of the resulting residuals, you can see that, well, normal distribution fits nicely here. And naturally, some of the observations, especially the ones where weird stuff happened, will naturally have, well, essentially a large deviation here. So now it's really up to us, right? So we can do with this acquired residuals data whatever we want, so we can go as far as we want into any form of statistical analysis. Let's say, for the sake of example, let's take the tails, right? So let's say the 5%, so plus minus 2 standard deviations away from the mean, and mark this as anomalies in this case, right? Again, this is completely in my control. I can make it as many standard deviations as I want. But in this case, I want to say, okay, 5% seems like a reasonable number. So you see here, those are the residuals that are marked using this approach. And if we project them back onto the original time series, we essentially get this. Right, so the idea is we, again, broke down the whole thing into a reasonable trend, a reasonable seasonal pattern, and everything else that didn't fit, we see how much it actually deviates from what we consider normal. And you can actually see that the mark points here sort of make sense, right? So we have this weird summer here, we have this weird winter over here, and some other things that are perhaps noteworthy, right? If you want to be more conservative, you can further adjust this rule to accommodate more points, essentially. All right? Again, we can talk about this approach forever, but what I think is important is the essence of what we're doing, right? So separating predictable part from the unpredictable part and doing the types of analysis that inform us of what is actually going wrong in the latter. Yeah, so to summarize, right, so we did a huge step now to be a little bit less arbitrary, and now we are more robust to past anomalies. That means if a lot of strange stuff happens in the past, it doesn't affect my anomaly detection too much, right? What is important to know here, well, in my example, it worked pretty well, but sometimes this sort of automatic filtering doesn't really work, and you see that the composition doesn't make much sense, and then naturally doing further analysis with it isn't really so reasonable. All right, well, let's talk about the third and perhaps my favorite in this case, which requires a bit more effort, but gives you the highest possible payoff probably. So that is essentially going properly into time series and building a form of long-term forecasting model and using that to actually, well, say, well, what is here normal and what is here beyond that. Now again, what kind of model we choose here, you can decide, right? So that's kind of a separate subject in a way. I'll show you again probably a both effective and relatively simple way to acquire a decent long-term forecasting model. What is essential here is now we're not doing some sort of arbitrary automatic filtering. We're actually doing proper modeling, right? So it'll be a mathematical model that we're fitting behind this time series, and we're analyzing things on top of this fit. But ultimately, we're not doing something too different from the previous approach. This is why I also said you can still take the residuals from this procedure and do the same type of things. Just the amount of effort you need to put to produce this model will typically be somewhat higher. Well, for the sake of time, because again, probably training a good time series model can take a whole separate lecture of its own. I'll show you the results that you can acquire from Profit. Maybe if anyone has done time series forecasting, you've at least heard the name, right? Pretty decent long-term forecasting package from Facebook originally. Essentially what it does, it, with relatively low effort, produces a fairly decent long-term forecasting model with benefits such as I can easily get confidence intervals, nice fits, nice plots. And I can say from experience, like I can beat this model, but it's not that this is stupid by the first construction, right? So I will often need to put substantial effort myself to produce a model that is more performant than this, while the amount of effort you need to put to train this is really just that. Again, don't worry about this. I will share the code so you can look it up if you haven't seen it before. But essentially what I've done here is produced a model fit over here, which contains what's important, all sort of different types of seasonality, which the model here detects automatically. So we'll decide, okay, do we want the weekly, monthly, or anything else? Does it make sense? It will also incorporate things like trend breaks and even holiday incorporation, so you can go quite far with it. But again, my interest here is not the model itself. My interest is how can we use this to detect anomalies, right? So let's say you use this approach or any other approach to have a decent structural fit, right? And you can evaluate this model and say exactly how good that is. Now, on top of this, we can essentially use any notion that we've learned before, and in this case, we have this nicely available confidence boundaries already, so we can see how this projects on the last year, right? So, nice thing about this long-term forecasting models is that we can keep them running as long as we want, so obviously for the whole next year as well. So we can see here that actually most of the things kind of do fit, but then the winter here is really kind of out of the bounds, right? And if you look at it, it sort of makes sense. It does look like we were going down and shrinking a little bit while something strange really happened in that winter. And what I like here is that, well, again, provided that you have a good model, the definition of what we call anomaly here is really quite more robust than anything else we've seen so far, right? Because that means we have a structural definition of reality over time, and something that fundamentally deviates from this reality is called an anomaly, right? So it's much harder to argue with this type of finding compared to rule-based, for example. All right? So to summarize this one, right? So while this does require a bit more effort, this is probably so far the most robust and reliable approach to acquire the anomalies in this case. Provides a nice representation of what we call normality, right? We can project it for any amount of time in the future, provided that the model is good. And what I'm not going to show here, but you can do this as an exercise, just do the same error trend, seasonality decomposition. Profit also allows you to do this quite easily, and then you can play around with the residuals and see that the same approach works quite well. And the last but not the least, I'm not going to dive too deeply into it, but I always get a question, well, how about short-term forecasting, right? What if the problem is not so easily predictable in the long term? I don't know, we're doing something with stock market or something extremely volatile. Well, in this case, it's important to know that the whole problem becomes a lot more complicated, and everything we talked about is really more applicable for well-behaved long-term type of patterns, because there is a good definition of normality there. While in this case, it might be quite a lot harder, but let's say if this is the only tool available to you, let's say you want to train a model that is really based on, let's say, looking 4 points back and producing the next point, right? So it's really quite a different problem. What I think is important to point out here, that with any sort of short-term model, it doesn't synergize so well with the problem we're trying to address, right? Because the goal of such model is to predict tomorrow's value as close as possible. Maybe they do a decent job at it if we really produce forecasts on a daily basis, like I did over here. But to use this to detect anomalies really becomes quite complicated, right? I can't do better than some sort of local anomalies, and even if I do something like cumulative standard deviations and see where things fall out of it, typically this will kind of work in the opposite direction, right? So that means that if I'm dealing with a highly volatile problem where there's no notion of normality, just keep in mind that everything we discuss becomes a little bit more complicated, and overall you might require a totally different approach. So keep this in mind for simpler, better behaved problems, and not so much for the rest. All right, well, let's summarize. So here's a bunch of takeaways that we've seen from all of the chapters we've gone through briefly today. So ideally, we want a system that has not too many false alarms, is robust to past anomalies, while at the same time doesn't require an immense amount of effort and domain knowledge if we're just starting with it as a part of the problem we're dealing with. And probably, ultimately, the best solution would be a combination of simpler tools that have nice common sense and explanation that you can use, to somewhat more advanced tools like long-term forecasting models that provide a more robust definition of normality and will help us address a problem in a more structural way. Thank you.
So thank you a lot for the nice talk. We have some minutes for a few questions.
Thanks for the nice talk. So now you selected your model. How do you know the model is good, or how do you compare different models? So do you look at it and say, okay, this one is better, or Can you quantify that, and what do you use to quantify?
Yeah, so that's back to the problem of having a good model fit in the time series problem, right? So that's back to whatever approach you're using. So of course, just looking at it wouldn't be a good way. But let's say you're using, I don't know, a cross-validated time series, one of the scores over the, let's say, 5 cross-validation faults in the past, and you're using some form of metric that informs you whether the fit is good. That becomes a valid way to compare models, right? Unfortunately, to explain cross-validation in time series in 25 minutes would be an impossible challenge, so I'll kind of leave it for extra reading.
Thanks.
Hi. You focused on point-wise anomalies in this case. There are other types of anomalies, like, for example, gaps and whatever. What do you suggest in this case for other types of anomaly? Do you think we can use these kind of methods that you presented, or do you suggest something else or other approaches?
Can you give a particular example? Because it's quite
I don't know,
right?
for example, if you have like missing spot in the data, or this is easy, but, or if you have, I don't know, some points that are normal, but you expect it to be like a little bit different, but for a continuous more time, especially on the past. So for example, if the same sensors also failed last year or failed in the past and continues failing, what do you suggest in this case? Because this method can fail, for example, for profit.
No, that's true. That's a good one. So in general, I would say that's just kind of a next steps into making all of this more applicable to much more complex anomaly detection problems. But overall, I think most of the things we talked about are indeed extendable in this domain, right? So even rule-based, you can think of indeed like this sort of conditionality, like if the sensors didn't fail, or if, I don't know, let's say the detection of past viewpoints as an anomaly affects the probability that the next point is anomaly, right? So a bit more conditionality. But most notably, probably the structural fits, right? Because that still makes sense overall, whether you look at points or the whole regions, right? Because what's important, it provides you the notion of normality against which you're comparing. So I would say how you're comparing is more of a how you use it, but the approach overall to produce this sort of backbone would still remain the same.
Okay.
All right?
Yeah, maybe a quick question. So you're talking about here about anomaly detections, let's say in the value dimension, right? So how would our approach change if we're interested in anomalies in like event times on the time axis? So let's see, we're expecting the event to come at a certain rate, and then we see shifts in time, like.
Yeah, so that, again, kind of a difficult question to answer in 30 seconds, but let's say one thing is change point detection, right, which is a bit different. Maybe just have some read into it, and Profit has some nice built-in tools, essentially seeing if event triggers, let's say, trend break or something like this. That would be one way to look at it. Another way is to first detect anomalies and then compare them against some sort of events. Like in this case, you can look up the forest fires, and if you see a match, that gives you an additional validation that your anomaly detection tool is indeed valid.
Okay, unfortunately, we don't have time for another question, so you can reach the speaker afterwards. So let's give another round of applause for him. Thank you.